Oh. I missed one and there were three and I got it. Good. Nice.
So what are you guys talking about?
Bible test? Yes.
Oh, I haven't ever heard you guys talk about Bible test.
Well, this is, it was
That's because we've only had two. This is terrible.
Oh, yeah, quizzes make up most of your grade 8 or what?
Yeah, we waited every week.
Yeah, but are they weighted more than that?
I don't think
Well, we
so.
have a test later because
Alright, so today we are going to talk about molecular geometry. Okay. Alright, this is my favorite acronym, the VSEPR theory. The Vesper theory. The Zephyr theory. Okay? The valence shell electron repulsion theory. Okay, this is the theory that suggests how molecules are going to arrange themselves in the shape that they will form, or the geometry that they will have. And it's all based upon one physics concept or one physics principle. Repulsion. Now, I started doing this idea when we were doing Lewis structures, right? I tried to show that electrons repel each other, so they're going to be as far away from each other as possible. Okay? So, when we start doing 3 dimensions, it's going to act the exact same way. They are the bonding pair, the lone pair, those guys are going to repel each other, so they're going to try to maximize the attractive forces and minimize the repulsion forces. Well, minimizing the repulsion force is going to mean get the negatives as far away from the negatives as they can possibly be. Make sense? So we're going to talk about how we're going to determine the geometric structure based on this particular property. So we need to define something. We need to define what is considered an area of electron concentration. Your book might talk about it as a region of electron density. That's referring to the same thing. Okay? So, there are 4 things that can be considered one region of electron concentration. A lone pair is a region. A single bond is a region. A double bond is still one region. And a triple bond is considered one region. So, let's see. Let's do this guy. Based on those 4 things that are classified as regions, how many regions of electron concentration or electron density does this particular thing have? Now, let me make one. Stop. Let me make one thing that's really important. This is, we're only going to look at the regions around the central atom. Why do you think it only matters the regions around the central atom?
That's where the between nucleus is. And it's that's that bonding. No.
It's not as, don't overthink this. Don't overthink this. It's where everything's going to pivot. Right? So we want to know around the central atom how the repulsion is going to go, because these things are going to be far enough away from your pivot points that they're not going to impact it. Okay? So imagine that this is your central and everything's kind of moving around that central particular region. So that's going to change how you would answer this. So I wanted to say that before I asked the question. How many regions does this have, Tanner? 2. But Mr. Kramer, isn't there a triple bond? Doesn't that mean there are 4 regions? No. So what I'm trying to say here is a triple bond is one region. A double bond is one region. A single bond is one region. Are you getting the picture here? Is this area a region? Yes. Is this area a region or a location? Yes. Okay? So it has 2 regions of electron concentration. Now you're probably wondering why do we need to know that? Well, we're going to progress and we're going to talk about why.
So there would be 2, not 3.
Yes, 2 regions. Yeah, because we're not considering that because it's not around the central atom. So what is the most you could have for regions? 4. 4. Okay, so it's most you get. Alright? Alright, so here's what I want you to do. I want you to describe how many regions of electron concentration each of these 3 guys has. Some of these you might be able to do just by thinking about it. And you might have to draw the Lewis structures if need be. When in doubt, draw the Lewis structures. Okay? Now, all 3 of these you've drawn Lewis structures of before, so it shouldn't be overly difficult to draw the Lewis structures of them. There are probably a few of you that don't need to draw Lewis structures, and you can just do it in your head. Done, Gabe? Done? Oh, I'm going to add this to it.
Is that because you just heard the same signal?
No. I didn't hear you say that. So I also want you to identify how many sigma and pi bonds each of these guys have, which, once you have the Lewis structure, it's not too difficult. Rachel done? Is that it all? Morgan? A++? Quinlan? Got it? Okay. I don't want to go too fast, so I'll make sure everyone gets an opportunity to attempt this, make sure we're getting it. I don't think this is an overly difficult concept. I think you guys will find that molecular geometry isn't that bad. There's a little bit of memorization that you'll have to do, but other than that, it's pretty straightforward. Okay? Tanner, could you tell me how many regions this guy has?
4.
Could you tell me the bonds? Sigma pi? No? Brevin?
4 sigma.
4 sigma? Why is it 4 sigma?
Because there's 4 single bonds and single bonds and sigma bonds.
Yep. Okay. Natalie Benitez, how many regions does that one have? 3 regions. Could you also tell me the sigma and pi bonds here? Did you say 3 and 1? That's out right here. Agree or disagree?
Agreed.
Agree? Okay. Rachel, how many regions does this one have? 2. And how many sigma and pi? 2 and 2. Questions? Kind of reviewed sigma and pi a little bit. Okay, if I ask you how sigma's orbitals overlap, would you be able to tell me?
The
Ends. Okay. All right. Which one doesn't happen on the bond axis? Pi bonds. Okay. Which one's not the strongest? I'm trying to ask questions in a little different format, just to you're not seeing the exact same.
So those are symbols that we use when we're talking about sigma and pi?
That's what, yeah. That's the sigma symbol and the pi symbol. Yeah.
Do we have to know the symbols?
Is that hard?
Yeah.
No, I guess not, but I was just wondering if that's.
I mean, I feel like you guys all know pi. The only one you have to worry about is sigma, but that was
Which
kind
is
of a
a
fun one to
cursive
draw
O.
anyways. So, okay, I talked about this yesterday. I talked about the hybridization, and I know that you guys are a little bit confused, or, you know, you acted like this was so deep, which is not as deep as you think, but hybridization. We talked about how if I were to do the molecular orbital notation for carbons, it would look like this. Remember this from yesterday? Okay? And we said this poses a problem because we know carbon can have up to 4 bonds around it.
5.
Okay? Which means that somehow this cannot be paired. Because you cannot overlap the same orbital twice. Does that make sense?
But there are 4 more arrows left that you can draw.
Okay? So what ends up happening in this case is that they get hybridized. This is what that other theory was suggesting, is that when things bond, they actually form completely new orbitals in the process, and they're hybrid orbitals of the existing ones.
Wait,
So-
so hybridization.
Sure? Answer your question in your own head?
Well, yeah, I was thinking that it's just based off of we only do hybridization because of that model.
That's not the only.
Yeah.
Okay? Now, what ends up happening is we have 4 orbitals here that are of different energies, but when we look at experimentally, these bonded overlapping orbitals all have the same energy. That's another reason why they had to have a new model, because we know 2s and 2p have different energies, correct? Which one's lower in energy? S. But when I look at this particular guy here, all 4, what this theory would suggest is that these 4 bonds are not all the same energy. Do you see what I'm saying? Okay? Well, when they do the experimental results and actually figure out what the bond length is and the bond energy is for these guys, they all have the same length and they all have the same energy, which suggests that they all have to be overlapping with the same energy orbitals. And so they've come up with this theory that new orbitals get formed, and it's a hybrid of the 2. So this is why they say 4 orbitals, because we had 4, but there were 4 different energy orbitals. 4 equal energy orbitals that are hybridized, and they say sp3 is just referring to an s hybridizing with 3 of the p orbitals. Does that make sense? And there are 4 of them, and they say that then this allows to have 4 equal energy orbitals that overlap, giving us the same energy bonds at the same bond distance or bond length.
And then sp3 because there's 3 p's left.
3 p
What's that
orbitals.
one s?
There is, when you take advanced chemistry, there's sp2 and sp. What ends up being is, like sp2, you have 3 sp2 orbitals, and then you have 1 unhybridized p orbital. sp, there are 2 sp orbitals, and it leaves 2 p orbitals unhybridized. Okay, so it's only the ones that are involved in bonding that result in your hybrid orbitals. And I know this is a little bit next level, but it's still good to at least introduce it, so if you do go on, it's not like I've never heard of it ever before. It's always good just to kind of go a step further. Okay, am I going to ask you to show the hybrid orbitals or anything like that? No, but I do want you to know what the process is. Okay, the big picture here is that when things bond, technically their orbitals don't just overlap, they form new hybrid orbitals that do overlap. Okay?
So they look different than the p orbital.
Yep. Yep. Yes, they do. All right, let's get into the geometry here. Okay, and then at the end here, you'll see a list that'll have all of these. So bear with me as we go through this. Okay? All right? So, CH4. Okay, and assuming you would view these as the bonds here. How many regions does CH4 have? 4 regions, and all of those regions are bonded regions. When you have 4 regions and all 4 are bonded, it has a tetrahedral shape. Now it's hard to show the 3-dimensional shape there, but it's going to maximize the attractive forces and minimize the repulsion forces. So the angle between all of those, I don't know if in your book it actually gives you the angle. Let me look. I know what advanced chemistry book it does.
Like the angles and degrees.
Yeah.
How do they do that?
Couple of them.
It'd be
Math.
180 divided by 3. based on that calculation. I was about to say, how can you measure that?
It's
It's
a
three.
well, it's a three-dimensional one,
Yeah, it's
so.
3D, 60 degrees.
So where am I here? Let me see if they say in your book. I know they do in the advanced geometry book, but the only ones they give the angle for are the bed guys. Alright, I'm not gonna make you know the angles. Alright? So let's move on. Next one. Still the same number of electron concentration here. Still have 4 regions of electron concentration. However, not all 4 of those regions are bonded regions. There is one region that is a lone pair, and so we would say 4 total regions, 1, 2, 3, 4, but only 3 of those regions are bonded regions. It's going to be a little different shape because bonding electrons repel a little bit differently than non-bonding electrons do. Okay?
They repel more.
I don't know off the top of my head. I can't remember. Okay? Then, 4 regions again still. This is your water molecule. 2 lone pairs, 2 bonded regions. So 4 total regions. 2 bonded gives us a bent structure. Not a linear structure, a bent structure. Okay? This is why we write H2O like this and not linearly. Linearly, is that right? Grammatically correct?
Grammatically correct.
Okay? Alright, now this one is difficult because what is your central atom here?
There it is.
Okay, so when we're talking about regions of electron concentration, we're usually referring to the central atom, correct? Right? Well, there's no central atom here, so you're going to assume the one that has the most regions is your central atom in a situation where you only have 2. Does that make sense? Okay? Alright, then there's 3 regions. There's 2 regions, okay? So here would be the structure of that guy. 3 regions, yeah? All 3 of those regions are bonded. Trigonal planar shape. Okay, I know it's hard. What was that? What is that shape? I don't have a Hall graph to show you, but you can look in your book and find out.
Has anybody invented a hologram yet? Something like it.
Oh, I'm sure they have something like it.
Like a projector, but they can.
I would love to have that. That would be sweet.
I still.
I don't have one. I don't see one.
A big expansion, but I'm school for free.
Yeah, they don't have a shape of trigonal planar.
Sure.
It is down.
One.
I'm sure we can look it up. Sure. Okay. Now we've got 2 bonded, 1 bonded. Okay? And then if we have 2 regions, so like here would be CO. Okay, that's going to have only 1 region, or sorry, 2 regions and 1 bonded. And that guy's going to act like a linear guy. Now, I'm going to give you the whole picture here. There it is. You will have to memorize this.
Great.
But I promise you, it's not that difficult to memorize because there's nice symmetry with this. What do you notice?
4,
4 fours, 3 threes, 2 twos. What do you notice about this?
4, 3, 2, 1, 3, 2, 1, 2.
But we can memorize all the shapes.
All right, let's do an acronym for it. This is the acronym they came up with last year. We can come up with a new one if you want. Tight, pants, be lame.
That's your one.
No, I'm like.
Tight, pants, be lame, lame, lame.
Right.
Tight pants, be lame, tight pants, be lame, lame, lame. Now, you will have to know what each of them, but we'll do them enough that you won't, first of all, linear is up here 4 of the, what is it? 4 of the 9 times. Bend's up there 2 of the 9 times. So you really only have to know 3 other ones outside of linear and bend. Tetrahedral, pyramidal, trigonal planar. It's really not that bad, I promise. I can make you go back and memorize the polyatomic ions if you want.
No.
I can probably don't do that right now.
Which you will have to do next chapter, just let me know.
What are those?
I can probably do the chart right now.
You probably don't even know what those are yet.
What are those?
Okay? So, so in order to figure out the shape, you have to be able to identify how many regions it has, and then how many of those regions are bonded. So let's do it. Are you good with that acronym, or do you want to come up with your own?
Tight pants feeling.
Okay.
It's fine. That's terrible, but.
Tigers, panthers, bears.
Tigers, panthers, bears,
White
llamas.
hands become.
Tigers, panthers, bears, llamas. Tigers, panthers, bears, llamas, llamas, llamas.
Try
Best
pepperoni
thing
burrito.
ever.
Try pepperoni burritos.
Loser.
Loser. Try pepperoni burritos, loser, loser, loser. See, you can come up with an acronym pretty easily with it. Okay?
Try ponchos.
So, here's what we're going to do. Then we're going to do these four. I'll do the first one with you guys. Shh. We're going to state how many regions of electron concentrations there are. We're going to predict the shape. We could also show the bond polarity. If you want to.
No thanks.
Okay, I can do sigma and pi bonds.
Does it say that in the directions?
Does it? We have a verbal agreement.
He is the direction.
We have a verbal agreement here. All right, let's do this one. Oxygen. If I remember right, this is one guy that has resonance.
Oh,
I still don't understand.
Probably should do this.
it's a triangular, isn't it?
Ha-ha.
Or not?
Ha-ha.
It's linear.
Now, my Lewis structure is not going to show the correct shape unless I knew what the shape was before I started drawing the Lewis structure. Does that make sense?
A couple of those atoms out.
Okay? So, here's the problem. Technically, this oxygen is stable, but these two aren't, and there's no negative charge here, so I cannot give it an electron from an outside source, which means I'm probably going to have to form a double bond somewhere. Well, let's see. Let's go like this, and just form the double bond here. Now, if we look, that's stable, but this has too many electrons, doesn't it?
So just keep that one over the other one.
Keep that one?
Yes.
Yes.
Let's go down
Okay?
over there.
So, electron's going to go over here, everything's stable.
Doesn't make
Oh.
sense.
Why?
Why don't you just do a triangle? Do one single bond.
Because that would not maximize the repulsions, or minimize the repulsions.
Here's his question.
Linear is going to minimize the repulsion more than a triangle shape would.
They're all the exact same under a triangle.
Yeah, but remember, we've got it. You're right. They're all the exact same oxygens, but you have to minimize how much repulsion it has. There's going to be far less repulsion in a linear shape than in a triangle shape. Okay. So, how many regions here?
2. Or they're not. I don't know.
2.
3.
Oh!
Because of the pair above the middle one.
1, 2, 3 regions.
Wait, why is that?
Because lone pairs exist as a region.
Oh, lone pair's on the, oh yeah.
On the central
On the
atom,
central.
Ah, okay, missed that one.
3 regions. How many of those regions are bonded?
2.
Okay, so
So
let's
it's
see.
meant 101.5. Oh.
Bent 120. Okay, now you have to, write out your tight pants be lame or tacos, burritos, whatever.
Try pepperoni.
Try
burritos.
pepperoni
Try
burritos.
ponchero burritos.
Okay? So, if we look at this, we got 3 regions, 2 of them are bonded. We look at our list, or once you have it memorized, you would find that this is going to be a bent 120 structure. So if I wanted to be accurate, then I should probably show this in bent form.
Try pulling those loudly.
Try what? Try what?
Try playing bows loudly.
Boats.
Oh.
Try pulling.
Loudly, loudly.
Try Try pulling both loudly, loudly, loudly. I do that 3 times loudly, Marty. Go ahead. Alright. No!
Yes!
No!
Yeah.
No!
Go fast! Go!
Okay, come down.
Okay? Two regions.
2 regions.
2 bonded.
2 bonded.
It's linear.
Linear. Lame.
Lane.
Okay?
Shut up!
This side.
4.
4 regions.
What is that one?
How many bonding? I just gave it to
He's
you.
like, oh
Three.
my.
Bonding. Wow, that's awful.
Last one.
Which one is that? What's a 3? What's a 4-3?
Pyramid.
That's a pyramid.
Pyramidal.
I would